Welcome to this video on deep spiking neural networks. My name is Wolfram Gerstner and I'm one of the co-authors of the papers of Anna Stanojevic that I will present in this video. Often I hear training spiking neural networks is difficult, and I hear spiking neural networks perform worse than artificial neural networks. What I would like to show in this video is that if you compare deep spiking neural networks with deep artificial neural networks, then there is no performance gap. Before I start, let me mention three common misconceptions. The first one is standard backprop is all you need. Well, if so, why use batch normalization? Why is initialization important? If so, why is there a vanishing gradient problem? The second misconception is calculating derivatives gives the gradient. The answer is no, because if you do this, you assume the Euclidean metric. Now, what do I mean by metric? If you have a coordinate system xy, you may want to transform it to a different coordinate system with radial coordinates rho and phi. And then in this new coordinate system, the actual dependence on the parameters or variables rho and phi is different. Now, if you think of an application like weather forecast, then not all input parameters are the same. One input might be wind speed, another one temperature. They have different units, they have different meaning. And that also means that the weights connected to these inputs have different meaning. They have different units. In particular, independent of the application, threshold variables in artificial networks have a different meaning than weight variables. And the metric allows you to take account of this and many other things. The third misconception is because of the sharp threshold, gradients in spiking neural networks do not exist. And well, no. There's a confusion between a threshold in the perceptron and the threshold in the spiking neural network. There's a confusion between discrete time models and the continuous time models that we have with spiking neural networks. And let me start with this first misconception. So, what are these spiking neurons? Let's look at this little figure here. Let's assume a spike arrives. This spike causes a response, that's the blue line, and this response has a name. It's the postsynaptic potential. What you measure is the membrane potential U. It's called postsynaptic because the connection point is called the synapse, and the synapse has the weight of the connection. So this was with one spike. Now let's assume that we have several spikes that arrive one after the other, and then the picture would look like this. Each spike contributes one of these postsynaptic potentials. There's no way yet to talk about output spikes. Output spikes arrive if you compare this potential with a threshold theta, and this threshold crossing happens here, and that's a moment when a spike is emitted to many other neurons. Spikes are events. They are events in the sense that the form of the spike is very standardized and it does not contain any information. Spikes are triggered at the threshold, and so the important information is that is the moment of spike firing, the moment of threshold crossing. And now after the spike, we start again at a lower value. So there's an effective dead time, and then there's a reset, a restart at a lower value. So spikes are events. They are triggered at the threshold, which defines the firing time, and afterwards there's a reset, there's refractoriness, and so forth. Now the spike response model, which is a framework that includes the leaky integrated fire model as a special case, is an example of a formal phenomenological model that works directly with spikes that are generated by threshold crossings. It's a phenomenological model because we don't worry, for example, about the ion channels that open and close, the biophysics, the ions that flow in, that really make this spike happen. So let's look at the math that goes with this spike response model. And this is also the math of a generalized leaky integrated fire model. And it's also the math of a non-leaky integrated fire model. So what does this look like? So what you measure in the experiments is the voltage, membrane voltage UI. I is the index of this neuron I that we currently consider. And now each incoming spike, and that's the firing time here of some other neuron, each incoming spike causes one of these postsynaptic potentials. And these postsynaptic potentials are weighted, and I sum over all neurons that connect to this neuron I, and I multiply with this weight, Wij, and I sum over all firing times. And the firing time index here runs from 1, 2, 3, 4, 5, and so forth, because every sending neuron, every presynaptic neuron could emit several spikes. So that's the input part. That's how we treat the input, the effects of the input. Now let's look at the other term. This other term is the term that describes the reset and refractoriness. And this here is the firing time of neuron I. It's this neuron. And we assume that up to time t, this neuron has already emitted n spikes. So this TIF, f equal 1, 2, 3, up to n. And then the next firing time of this neuron I is at the moment when this voltage reaches the threshold. And this defines the next firing time, which is now the spike with the number n+1. And so this is the framework of the deterministic spike response model, often called SRM. Now let's look at gradients in these models. So we look at this generalized leaky integrated fire or spike response model, and here's my voltage again. It's exactly the formula that I discussed on the preceding slide. And now I told you the next firing time is when this voltage UI hits the threshold theta. And so this would be this moment here. But now suppose I have another I have my input spike from neuron J that arrives not at this time, but a little bit earlier by a time delta J. So delta J is negative here. Now that means that this final postsynaptic potential happens a bit earlier, and therefore the firing time is also a bit earlier. So what is the new firing time? I put in this change for this of the firing time of this neuron J, delta J, and let's now look at what this makes to the threshold crossing. The moment of threshold crossing defines the next firing time, and this next firing time, as you see, depends on my time shift delta in the input. So let's plug in the formula, the equation that I have up here. So you see that this equation up here depends on the time explicitly, and then it also, but this next firing time will depend on delta. And then this equation up here also depends on delta explicitly. So the threshold itself doesn't change. So if I take this condition of firing, then I can say, let's look at the change of the voltage as a function of delta J. This is the change of the firing time as a function of delta J. And this was equal to theta. And therefore, I can take the derivative on the other side, and I get 0. So this is 0. Now I evaluate what I have here on the left-hand side. And I take the derivative with respect to t and then apply the chain rule, dt n plus 1 d delta j. And then I have to take the explicit derivative with respect to the explicit delta that appears in the equation. And since I have a minus sign in front, it gives minus wij epsilon prime. I solve for this term here, and this gives the final formula. Now let's look at this formula. What is u prime? U prime is the slope of the membrane potential at threshold. Epsilon prime is the slope of this postsynaptic potential at the threshold crossing. And what I have here on the left-hand side is exactly the backprop term. It describes the shift of the output spike caused by a shift of one of the input spikes. Therefore, we can directly calculate the gradient. We can directly calculate the terms that we need to set up a backpropagation algorithm with spike coherence in continuous time. So this is my result. We find a gradient despite the sharp threshold in spiky neural networks, and we have interpretations, the slope of the postsynaptic potential, the slope of u of the voltage at the threshold crossing. And as you have seen, this is a straightforward calculation. I did this for the first time in '93 in the context of collective oscillation, but at this moment I was not interested in backpropagation at all because I thought it's not relevant for neuroscience. And then Sander Bothe was the first, to my knowledge, who actually calculated this and used it for backprop in the context of a time to first spike code. And this is still an active field. There are also papers out of the recent years. Now let's take this formula that I just derived and consider a special case. This is a special case of the spike response model. It's a non-leaky integrand fire model with triangular postsynaptic potential epsilon. So triangular means if a spike comes in, the membrane potential is deviated with a triangular shape. So this is my spiking time. If the spike comes earlier, if the input spike comes earlier, then this spiking time is shifted, and I can directly use my formula here on the left-hand side. For the triangular EPSP, postsynaptic potential, I assume that the derivative is 1, and therefore I get this simple expression that the shift of the firing time is just the weight divided by u prime, where u prime is the slope at threshold. Now, assume by chance the slope at threshold is u prime equal 1. Then the formula is super simple, and the derivative is just the weight itself. And I remind you, this derivative, the shift of the spike time, that is the backprop term. Now let's do a comparison with the artificial neural networks, and let's consider a ReLU network. A ReLU network has variables x, I, this is neuron I in layer n. There's a nonlinear transform, and this nonlinear transform is piecewise linear, so it's just the sum wij xj of the sending neurons in layer n minus 1 if this term here is positive, if this hi is positive, and otherwise it's 0. Now, I remind you of the derivatives for backprop. You get a derivative for this ReLU network, which is just the weight under the condition that we are in the first line. And this is the backprop term. Now, the backprop term means we look at the backward path, and what you see on the backward path is essentially the weights, but only for those neurons that have a potential or input drive that is positive. So the backward path is essentially a matrix multiplication, but some neurons are masked out. since the g prime, the derivative of this transfer function g, is either 0 or 1. And keep that in mind for later. So often we hear training spiking neural networks is difficult. Yes, but the reason is not that gradients do not exist. The exact gradient can be calculated easily. Then, what is the reason? And that will be the remaining part of my talk. So now I would like to show the equivalence of artificial neural networks and spiking neural networks. And this is a long-standing field of research. And Wolfgang Maas has in 1997 written 2 very nice papers where he shows equivalence of the two in a very general setting. Now I would like to work in this framework but be very specific and look at ReLU networks. And I would like to make three claims. The first one is ReLU networks are completely equivalent to a non-leaky integrated fire with triangular post-synaptic potential. Equivalent in the sense that I can select the parameters of my non-leaky integrated fire model such that it matches exactly a ReLU network. Second claim, the gradients, so these what I call the backprop term, these gradients in the ReLU network are exactly the same as those of a nonlinear integrated fire model with triangular postsynaptic potential and U prime slope at threshold equal 1. And third, all integrated fire models with U prime smaller than 1 have an exploding gradient problem, which is the mirror to the well-known vanishing gradient problem. So let's start with point 1, and we always use time to first spike coding, TTFS coding. That means each neuron sends out at max 1 spike. And we consider a layered feed-forward network, a deep network where neurons in layer n-1 send input to layer n, from there to layer n+1. So here is one of these networks, and I is the neuron index, and here is my neuron I in layer n, and then the spike time of this neuron is TIN. Now here I would like to emphasize n is now the layer index. I don't need to count the spikes of each neuron because a neuron can send out maximally 1 spike since I'm in the TTFS coding scheme. What is a non-leaky integrated fire model? You have a differential equation which describes the slope. The slope has a constant and then it depends on the input. And this input is a sum of step functions. And now if you insert this here, integrate this up, then you get a membrane potential, which is A times T, and each Wij, each weight contributes a triangular contribution. Now we say in addition that the simulation stops if U of t reaches the threshold, or if the dashed line here, which is for the case for the no input, reaches the threshold. And that means spikes cannot occur after this time max. So what is blended out here with this bluish color means spiking later than Tn max. Max, the latest possible spiking time in layer n are blended out. Later spiking is impossible. Okay, now each input spike contributes a change of this slope, and this gives this triangular potential that I talked about earlier on. So this would be the spiking time, the output time of this neuron I in layer n, and if there are more spikes arriving and the weights are positive, then this spiking time would occur earlier. So let's again work this out. So the dashed line sets the condition. Spiking can occur earlier. And importantly, later spiking is impossible. So whenever I would have only negative input weights, so it would be bended down, and spiking would not occur. So negative input leads to quiescent output. And now, first step, we note that this is very, very similar to the ReLU if condition. If positive, you get an output. If negative, you don't get an output. But we can be more precise. So theta is this slope factor times Tn max. And we think of a spike at this moment here. Now, if positive inputs come in, then the firing time is earlier. And we define the effective activation of the neuron as how much earlier the output spike occurred. And so this is the activation level AIN. And this is true with positive input. Now, in the case of positive input, we can then solve this equation up here. And what we find is that this output spike shift, AIN, or activation of the output neuron, depends linearly on the activation on the shifts with respect to their own earlier maximal firing time of all the presynaptic neurons, of all the neurons in the earlier layer n-1. Now let's look at this. In principle, this looks a little bit, the whole thing looks a little bit like a ReLU condition, except for one thing. So in principle, I could say whatever I have circled is the effective ReLU weight, except for one thing. This sum here runs over J prime, whereas J prime means the relevant inputs. Relevant inputs are those that contribute to spike firing. So these are two relevant inputs. This one here is an irrelevant input. It arrives, but after the output neuron has already fired. Now this also tells us that in general, this non-leaky integrated firing model with triangular EPSP is similar to a ReLU, but depending on in which sequence spikes arrive, the output, the effective mapping to a ReLU network would be different, since the output would be different, since the output depends on this denominator here, which is the sum over the relevant spikes. Therefore, and that was shown in a nice paper by Singh, Fono, and Coutinhoc, the expressivity of the spiking network that looks similar to the ReLU network is higher, because in fact, depending on the order of the input spikes, the mapping to the ReLU network is each time a different one. So, to summarize, this looks nearly like a ReLU network, except for the irrelevant spikes. Now, if you look at the terms that are circled in here, I just remind you, this is the slope at threshold. So it's not some obscure term, it's a term that's easy to interpret. And now let's exclude these irrelevant spikes. And this gives the first exact mapping. And the first exact mapping, we say that the slope at the beginning is 1. And then the first spike comes, and afterwards the slope changes. The second spike comes, the slope changes again, and so far. So now the trick to exclude irrelevant spikes is to say the postsynaptic neuron can only fire after the last presynaptic spike arrival. So presynaptic spike arrivals occur in this interval, and output spikes are possible in that interval down here. And therefore, I'm sure all neurons have fired before the first neuron in the next layer fires. Formally, it's convenient to say we artificially trigger neurons that have not fired before this point here. We give an artificial trigger so they are all out, they all have sent their spike. And if you do it like this, then it's just the sum over all the weights. I no longer have the distinctions between relevant and irrelevant spikes, and therefore I have an exact ReLU. And this weight, the corresponding weight of the ReLU network, is the original weight divided by this denominator, and this denominator is indeed the slope at threshold. So what we find here is I have an exact mapping, and the number of neurons in the spiky neural network matches one-to-one the number of neurons in the artificial neural network. So first claim, ReLU networks can be described by non-leaky integrated fire models with triangular postsynaptic potential, and this works if you have time to first spike coding, so there's maximum one spike per neuron. We have a layered feed-forward network in this example, and I have to make sure that neurons in layer n fire after neurons in layer n-1, and I've indicated how to organize this condition, how to implement this condition. Now the second claim is gradients in the ReLU network are the same as the gradients in a non-leaky integrated fire with triangular PSP and additional condition slope 1. So this slope 1 is the new condition that distinguishes point 1 from point 2. So how does this work? We said for this first version that the parameter a, which is the slope at the beginning, this parameter here or on the image, it's the initial slope, that this is equal to 1. But as a result, the final slope when they reach threshold is different for different neurons. So the different shades of green correspond to different neurons in this layer n of the network. And different neurons have different slopes. Now the slope is the denominator in my equation. So different neurons have different slopes at threshold. And now we want to construct a version where all neurons have the same slope at threshold. So what we now do is we say u prime is the final slope and it's equal to 1. We start with the a equal to 0. As before, we make sure that the postsynaptic neuron can only fire after the last presynaptic spike arrival. Spike times of the presynaptic neurons are in this interval. And then when I'm sure that that no presynaptic neuron can fire anymore, once I'm at t max n-1, I just adjust the slope artificially. That's easy to do in a model. It's easy to do even in a neuromorphic hardware. I adjust the slope to the desired value of 1. And so the slope is this denominator, as I mentioned before. The slope is now 1, and therefore the weight is the same. The weight between a ReLU network and my network with spiky neurons is the same. So I have a one-to-one correspondence and even the same weights. So I get exactly the ReLU formula, and moreover it's exactly the same weights. I don't have to remap the weights. Now let's look at the derivatives. Now neurons have the same slope at threshold. And what are the derivatives? The slope at threshold is 1. Therefore, for these variables A, I remind you, these are how much the spike is advanced compared to the latest possible firing time T max n. So this derivative is just the weight if the neuron is active. And this is the ReLU backprop term, which means the gradients are the same. Now later I will comment on this if condition. I mentioned already for the ReLU network, the backward pass means it's a multiplication with weights, except that some neurons are masked out. And the same mask happens now here for my spiking neural network. So let me summarize this. ReLU networks, and they can be mapped to non-linear integrated fire neurons with triangular PSPs, and there are many mappings. Now, if I have this U prime equal 1 condition, and that was my second version of the mapping, then I get perfect ReLU gradients, and here just the differential equations for these situations. The first one has not changed, and the second one is now always 1, and this is as soon as we pass the latest possible spiking time of the presynaptic neuron. The third claim now is that integrated fire neurons with U prime smaller than 1 have an exploding gradient problem. So let's look at these exploding gradients. What is the problem? I remind you of the general backprop formula. We calculate delta mismatches or local errors in the output. They can be positive or negative. And then we backpropagate these delta errors backwards. And this is the update formula. And now in a ReLU network, G prime is either 0 or 1. And so I get this simple multiplication with the weights if the neuron is active, and otherwise it's masked out. So this is the ReLU backprop term. And effectively, you can think of a matrix multiplication for each step of the backward path, except that some neurons are masked out. Now note that if I had chosen a piecewise linear network, but where the slope is 2, then, well, the multiplication of weights would have each step this extra factor of 2. And there's a risk that on the backward path, the gradients would blow up from one layer to the next. Now let's look at my spiking network. And what we do now is we initialize with standard SNN methods. And if you do this, then you see that with standard initialization, the weight matrix from layer n-1 to n is the red one. It has eigenvalues in the complex plane, which are these red dots, and they're all very well confined. However, the gradient matrix in this version 1 of the spiking neural network mapping has these eigenvalues that correspond to blue dots, and some of these eigenvalues have large real parts. And therefore, gradients blow up. If you multiply this and again across many layers, gradients will blow up. And the reason is neurons have different slopes at threshold. The slope at threshold is in fact the denominator of this effective connectivity. Now let's look at version 2 of my spiking neural network. As before, we initialize with standard SNN methods. The red weight is the weight matrix, the blue is the matrix of the effective gradient, and the points lie just on top of each other. And the reason is that the slope at threshold is now 1. So gradients no longer blow up because all neurons have slope 1 at threshold. So if I don't have this u equal 1 condition, I end up with exploding gradients, but the second model has this u equal 1 condition, and that means we can now apply textbook initialization as you read it in textbooks for artificial neural networks, for deep networks. We can use standard initialization that work for ReLU, and they also work for our non-leaky integrated fire model. They work for our spiky neuron model. And indeed they do. We check this. So the ReLU model is this, and this version 2 of the model where the slope at threshold is 1, the B1 model is just on top of this line. Well, but if we take the version 1 of the model, then the behavior is much, much worse. Of course, one could readjust initialization, but then after the first update step, if you apply your gradient updates, epoch 1, epoch 2, it gets bad again. So it's not easy to cure that. Please take version 2 of the model. Now we can compare the performance on a standard database like MNIST, and the first comparison is a 2-layer fully connected network, which means one hidden layer. Then we ran a ReLU network, that's the performance. We ran our spike neural network, really integrating the differential equation. The performance is the same. Then we have a couple of competitors that had lower values. Then we can do the same thing in a much larger network. For example, in this VGG16 network, performance between the ReLU network that we trained and the spiking network that we trained is just identical. And the same holds for other databases like the Fashion MNIST. More interesting is maybe the following application. Suppose you have some neuromorphic hardware and you're able to download a network download the network from the web, from some repository, and then you translate the parameters according to the rules that I set. And now afterwards, maybe the hardware has slight mismatches or not. Afterwards, you can fine-tune this network. Now, to be sure that it could be that the network that we downloaded is not optimal, we also allow for fine-tuning of the original network. And we fine-tune for 10 epochs, and we repeat this 16 times to get some statistics. And then you see that the ReLU network and the spiking network, they just have the same accuracy for CFAR 10, for CFAR 100, and then also for place 365. This is an alternative to ImageNet and avoids privacy concerns. And you see again, the numbers are just the same. More interesting is now the fine-tuning properties to exploit potential advantages of spiky neural networks. And one argument that you hear a lot is the energy consumption of spiky neural networks. And we just follow the standard arguments. So like others, we assume that energy consumption in neuromorphic hardware will be dominated by the number of spikes. And we calculate the spiky neural network sparsity, which means the fraction of spikes used to classify one input pattern. And then here on the right-hand side, you see the sparsity. It's very low, but we can make it even lower if we apply L1 penalty during training, and then you get down to below 0.3 spikes per pattern classification per neuron. Now, let's assume that my trained network, and we take the CFAR 10 network for this final application, my network would be implemented on a spiky neural network hardware. And then people have argued on real hardware you would have spike time jitter, and that means input spikes that arrive have an uncertainty. They might come a bit earlier or a bit later. And then we can increase this standard deviation of the jitter. And you see that if you directly use the network, it goes down. But if you allow for fine-tuning, you can keep up the performance at very high values, even though the spike jitter is rather large. A similar argument can be made for output spike discretization. This is now the spike that the neuron sends out to the next layer, and suppose we implement this network on neuromorphic hardware that has discrete time, then I would have to worry about how many time steps do I have per layer. And you see that even with 16 time steps, only 16 time steps, the performance is still fairly high. Similar argument for weight discretization. Maybe the weights only have 4 bits and not 12, and then the performance stays high. The final test is, you can say maybe it takes a long time to first wait for layer n-1 to finish before I start layer n. So let's squeeze everything together. And so 100% means full separation. Latency, which gives a long latency. If I reduce the latency basically by a factor of 5, I still get a fairly good performance. So I made 3 strong claims. The first one, ReLU networks can be perfectly described by non-linear integrated fire neurons with triangular postsynaptic potential. We used time to first spike coding. We looked at layered feed-forward networks. And the one condition we have to make sure is that neurons in layer n fire after neurons in layer n-1, because otherwise we could have irrelevant spikes. And then I said, well, there's one specific mapping which is super nice, and that's the one where the slope at threshold u prime is equal to 1. And if I don't do this, we have this exploding gradient problem. But if we do this, and we do this for the second model, then we can use standard initialization tricks from artificial networks. And obviously then there is no performance gaps. And we can do this even though only a small fraction of spikes per neuron per input is really is sent out. Now, we made some assumptions here. The first one is real neurons are leaky. This is a critique of this assumption, but the assumption was the triangular PSP. If you look at the leaky neuron, the postsynaptic potential would look like this, but the initial phase is actually very similar. Second critique, real neurons fire more than one spike, and it may look like this: first spike, second spike after reset here. Now I would argue, but we have not done this, that if you make sure that the u prime is equal to 1, in other words, you said u prime equal to 1, you just remove it from the formula, you remove the denominator, then you should be able to use standard backprop through time, BPTT, and still get good results. The third one is the network is slow since layer n starts processing after n-1 is finished. And again, I would argue it's not necessary. We can push things together, and moreover, you might be able to improve performance further if you neglect this u prime in the formula, which means for all active neurons, you set the slope at threshold to 1. 3 common misconceptions. Standard backprop is all you need. Well, weight initialization is important. In fact, it's important because of the vanishing gradient problem, amongst other things. And if we have our network of the second version, then the problems of weight initialization, the problem of exploding gradients has disappeared. Another misconception, because of a sharp threshold, gradients do not exist. Well, they do. And it's because initialization is important that you need some control of the exploding gradients, and this control is easy if u prime is equal to 1, as we do in the second model. And calculating derivatives gives the gradient. Well, No, that's true for Euclidean metric, and that's also the one I used here. But I said threshold variables are maybe different from weight variables. More generally, you have quite a free choice of the metric, which gives you a freedom of rescaling. And if I say ignore the u prime or set u prime equal to 1 for active neurons, then I exploit some of this freedom that the choice of metrics would give me. And I would like to thank Anna Stanojevic, who did the main part of the work, as well as Guillaume Belek, Stanislav Wozniak, Giovanni Angeliki, and here the two papers. And this question of metric is a paper of Johanni Prea and colleagues.